inviting me to come talk at this conference. And thank you everyone who's coming to this talk. So the main thing I sort of want to organize this discussion around is a certain conjecture that's been motivating my research for the last year or so. A bit more than a year actually. So this is joint with David Jordan. But I would say pretty distinct from what he told us earlier. So to give just the shape of this conjecture, we're going to have two main objects. One is going to be called the Jones polynomial, the color Jones. And this is going to go from integers to a function field Q. And then the other one is going to be what I'll call the quantum A polynomial. And this is going to be in a ring. It's going to look like this. It'll have two generators, and these generators will Q commute. And the conjecture is stronger than this, but one of the catchy parts about it is it says this acting on this space, this element in particular annihilates this. So this A acting on J equals 0 is the source of the name of this conjecture. All right, let me do the plan. So first I want to start talking about diagrammatics. We've already seen a little bit, and this in particular is going to be focused on this J part. After that, I want to talk about character varieties. And this is going to be the A hat part. And then to wrap up, I want to discuss the relation between them, which is this AJ conjecture. All right. I also want to say I wrote the talk to be like just under 50 minutes long, so we absolutely have time for questions. Okay. I want to start with diagrammatics. So for me, these are going to be diagrammatics of some category, some type of category. And this type of category is going to be called a ribbon category. And I'm going to always write this as fancy A. And sort of as I give this definition, I want to have a running example, which I think of as sort of the example. And this running example is going to be, I'm going to call it rib. And this is going to be the category whose objects, in a second, but the morphisms are going to be spans of, what are all the words I need? Directed, frame, graphs, and a space like this. So these are the morphisms. These things here get called ribbon graphs. And my objects I'm going to be thinking of as the boundary of these graphs. So I have something here, I have its boundary, and what it's going to look like is a bunch of points, and they can be oriented, and I'll think of them as living in this disk. So here's an example of an object. I could also have an object which is just no points. So maybe you would just draw that as the disk, and I don't draw anything. Okay. So a ribbon category, let's start with talking about its structure. So it needs to have a product.
You say spans of graphs?
Oh, sorry.
Graphs themselves are the spans.
Yeah, sorry, I should have said finite sums. So somehow I could have a graph like this plus some other graph. Which is something else. And just the endpoints. That's that question. Did I answer it? Yeah. So it's these. I have a product. And I have a unit. Here, what does this look like? My product is going to be induced by what you maybe want to think of as disjoint union And the fact that if I have two graphs like this, I can graphs embedded in it's like this, I can just embed it like this. So does this make sense? I have two graphs and I can put them. And then my unit ribbon is just going to be this empty object. Okay, so this, I want a duality structure. What this is going to look like is a couple of natural transformations. And then it's from it's going to be dual to the unit. And the other one is from evaluation, it goes the other way. So what does this going to look like here? My example. Make the word clean, I'm not going to draw the cylinder anymore. So my evaluation, I'm going to go from 2 points. One, oh no, this one's positive. Its dual is going to be negative. And my evaluation is just like this. I think someone asked David, and David was annoyed, but I'll just say my morphisms go up. So it goes from here to here.
No, that was flustered.
Maybe it's very similar. Okay. So, but I need the other one. Yeah, I'm junior enough to say stuff like this, right? So the other direction, I need to go to the unit, the 2 dots, and it's going to be this other graph like this. Here, so this one will be plus and this one's minus. I have some axioms on this. I'm going to just draw them. I'll change color. So the axioms are going to be some compatibility between these. And in this very nice graphical setting, what these axioms are going to look like is the fact that if I compose identity and co-evaluation, evaluation and identity, this is just the same as a straight line doing nothing, and that's the same as going in the other direction. And I have, so this is one orientation, but you can picture the strand is going down. It's still clearly obviously true. So that's what the axiom is going to look like. We have braiding also. It's one of my favorite structures in math. So this is similar going to be a natural transformation. V tensor W, W tensor V. What this is going to look like here is really something that could justify calling a braiding. It's just like this. Right, and I'm going to have some axioms on this. The first axiom is that I want this to be an isomorphism. And that means that this thing needs to have an inverse. And what's that inverse going to be? Well, I have this one. I want to undo it. So I'll do the crossing in the other direction. Right, and this is just isotopic to the identity. So that's one thing like this is invertibility. And the other one I want would perhaps take should draw it low enough to have space. Is celebrated. And it looks like this. So here's one side. Maybe it's a little harder to see, but what's going on here is I'm doing crossing and identity. Oh, I do my lines badly. But then here I get, you can see identity crossing. I'm just changing the order. And this has to be the same as doing it in the other order. This. So this picture, you can see that these are isotopic. I have this very back strand back here. And you can see here it's just below this crossing, and here it's above the crossing. So this is called Yang-Baxter. I have a version for it here. And then the last thing that I want is a pivotal structure, which I think of as also a natural transformation from V to its double dual. And I'll say in this story, what this looks like is this morphism, and it also has a diagrammatic version of its axioms that I don't like to draw. It's ugly. Okay, so I've set up this whole framework, right, of a ribbon category. It's a category with a ton of structure, and right? How I introduce this is talking about diagrammatics. And for me, what diagrammatics mean is I want to be able to draw pictures to describe the morphisms of my category. Right now, I've told you what a general ribbon category is. I've told you about my favorite example. I want to mix them together. How I'm going to mix them together is I'm going to do what I'm going to call colored ribbon graphs. Okay. So what this is going to look like is I'm going to take the same category. I'm going to do a subscript A on it. Now, we already saw this in David's talk quite nicely. Now I want all of my objects here to be labeled by objects in A. This I don't need to label anything. Here, see, I have a V and W and U. These are oriented. And just exactly as we saw, I'm going to have some morphism here. So I go through and I do the colors. Does this construction make sense? I think it's the second time today we're seeing it. Maybe people have had time to come up with questions since David's talk. So I have this. This is nice. I can start thinking about my original category in a graphical way, but I really want to be able to capture somehow the essence of this category in this sort of setting. And in order to compare them, what I want a functor. So this is, maybe this is, I'll call this theorem. It's definitely a theorem. It's from Reshetikin and Derive in the 90s. I forget exactly which year in the 90s. And this theorem is that there's a unique ribbon functor. And it goes from riv A to A. I call it RT. So it's unique such that RT of this isn't dual, and I have some other axioms too. So sort of RT of V1, V in, V in. Okay, so now I have a way of comparing these graphs that I've drawn to here. I want to say a nice thing about this is that such a functor really relies on this ribbon structure here. So I went through all of these axioms and I drew them here where they're obviously true, right? But I said there's a version of them diagrammatically here. So, or there's a version that's out right here. Like there's some equation here which mirrors this. And I need this structure to show up here in order for such an evaluation to make sense. Yeah. The first axiom?
Oh, no, RT on functor. On the left.
Oh, sorry. Yeah. So this one is that if I have a dot and it's negative,
Okay,
it gets sent to the dual of the thing. Yeah. Good question. Okay. So I had this nice bit of technology. The first thing I want to do with it now is to make a not invariant. So let's make a not invariant. Okay. Here's how I'm going to make my not invariant. First, what I'm going to do is let's say A equals rep Q SL2. And the thing I'm going to define is the colored Jones polynomial. So, so it's of not A is exactly the function in N, and it's given by this Verschutigten Dreiefunctor of my not colored by Vn. So this is my definition. I'll make a box. So I want to unpack this sum. So what's going on in this construction? First, I have an oriented framed knot. I'll follow our conference's proud tradition of only drawing the trefoil. So I have this knot, and I can think of this as an endomorphism in this category of ribbon graphs of the empty. Right? It has no top or bottom. So I take this, and then I can color by the n-dimensional irrep of so UQ SL2. So what I wrote up pi Vn. So now this is still an endomorphism, but it's in this colored ribbon category. Just draw A like this. So now I'm here. Now I'm in the setting where my Verschutigten Dreiefunctor makes sense. Apply RT, and I get RT kappa Vn in endomorphisms of A of the unit, which just is my base field, which in this case is frequency. So this, what I get is that this Vn, it's actually a Laurent polynomial. Here's some choice of normalization I didn't talk about at all. Are there questions on this construction?
When was this construction?
90s. You didn't ask, but it does work for other ribbon categories. This is just the one that is named and studied. You also didn't ask, but I'll pretend you did. If A is not semi-simple, you just get 0. Which is not such a nice invariant, but there is a way of fixing the construction using a technology called modified traces. So there's a version for non-semi-simple categories. Like that. Okay. So here I've defined 1/2 of this AJ conjecture. Now I want to switch gears and talk about the other ingredient in it. This is part 2. This is character varieties. And recall, this is this A hat I wanted to talk about. And I know we've already had these defined, but I didn't want to rewrite my talk over lunch. That would be a bad idea. So give and then another definition. So here's my definition is the G character variety of X. I'm going to write this chi sub G of X. And this is going to be, I'm going to look at homomorphisms from the fundamental group of X into G. I'm going to take this quotient. So let me label what some of this stuff is. I have this. So here G is a reductive group. X is some space. This double line means the GIT quotient. People also care about the stacky quotient version of this. And the action is conjugation. Sorry, this. I also want to introduce a little notation. So I have this quotient. Before I take a quotient, I have this space. I'm going to call this RG of X. It comes up in the top. So I have this character variety. Let's do an example. So the example I want to do is the SL2C character variety of the torus. Right? So this is just, it's going to be this representation variety of the torus, mod G. So representation variety, I'm looking at the fundamental group of the torus. It's just Z squared. So Z squared, SL2C. Still modding by SL2C, like this. So let's think about this. Z squared is a billion. SL2C isn't. There's no other relations between the generators of Z squared. So what I'm going to get here is just elements, matrices that commute. The A, this, and still up to this SL2C action. So these things commute, which means if I'm allowed to conjugate them, I can get them into a Jordan canonical form at the same moment. A bit of the magic of the GIT quotient is I don't have to worry about higher Jordan blocks. I just have to worry about diagonals. So what this is going to look like is pairs of diagonal matrices, determinant 1, like this. And this GIT quotient has mainly gone away, but I still keep part of it, which is a Z mod 2 action. And this is the action that tells me there's really no difference between if this was lambda or lambda inverse. Right? So this is my third variety. And this just looks like C star across C star. This Z2 action.
Now you're gonna sit Clark.
Literally.
I'm not that easily upset.
That's funny. I actually thought they meant you wanted me to write the Yeah, I'm American, so you think we'd do the same. I don't know why. I don't know what I used to do. Okay, but here's another example. It's maybe a little safer.
So is there a then diagonal action? How can you describe the Z2 action on C star times C star?
Yeah, it's like it's sending an element to its inverse. Okay. So now let's think about a general reduction group. I have the maximal torus in here. And I want to compute, or not compute, but I want to argue what this is now. So now I'm looking at the character variety. I have this action by conjugation, but everything is commutative, right? So my quotient falls away. And now what I have from the same argument is I just have like pairs of commuting elements in a commutative algebra. So this just looks like T cross T. And in particular, for the case that we care about, this connection is just C star and C star. And perhaps you've already guessed, this is the Weil group. This is mod 2. Okay, so I've given you a definition, I've given you two examples. But this talk is about polynomials. So now what I want to do is talk about how to get a polynomial. And this polynomial is what I'll be calling A. So first, it's going to be a polynomial associated to a knot. So I'll have K, my knot, sitting in S3. I'm just going to name its knot complement because it comes up a bunch in sub K. This is S3. Some little open neighborhood of my knot taken away. So there are going to be two tools that I use. They're not really fancy. One of the tools is that I have a torus included in my knot complement. This is just the boundary. Right? This is like the dumb fact that no matter how bad your knot is, it's still a circle. So that's one tool, and then the other tool is that I have this this T sitting in G, this kind of commutative subpart. Okay. Are there questions on this?
I can ask a question. It's probably a stupid question, but I just noticed that in example 1,
Yeah.
that thing has like at least I think that thing has like a derived announcement or derived version. Do you know if that's something that sort of
People care about.
care about? Yeah.
Yeah, I know it is. I don't know a lot more besides that.
Not
Does
it's
that interact at all with derived skein? Yes, derived version of this.
Yeah, so yeah, then all these moduli spaces, you can consider derived analogs of them.
but it doesn't affect the invariants that you look at now, right?
Well, this will be the zeroth homology of whatever derived thing you make.
Yeah, I haven't seen a derived version of this construction. What's the next question? Are there others?
Here, G is still SL2C. G is still SL2C, or is it from J?
Yeah, so this part doesn't need to be SL2C, but this part is SL2C.
So the
So this is true, but the A polynomial itself is defined for SL2C.
what's this?
Oh, so this tool is just, so this first one is just the fact that the
That's
boundary
fine.
is not complement of the torus.
Yeah.
And this is reductive groups have a maximal torus. So it's,
Okay, so it's any reductive.
yeah. So this is general, but I haven't. They're like, actually, the invariant I'm about to define, there's a lot of like algebraic geometry that went into proving that it is actually not invariant. I don't know if that's been done with general G. This SL2C. Okay. All right. Maybe. Okay, so now what I want to do is use all of this to build not invariant. So let me talk about what we have. First thing I'll do is SL2C of this knot complement. Right, my knot has to be somewhere. This can be very high dimensional. It can be super singular, unreduced. It's not a very nice variety. What I'm going to do is go into the variety that I've talked about. I'm going to push forward along this SL2C of just the torus. So this one's, I have a much better grip on it. So I have this, but that's not good enough yet for my construction. What I'm going to do is I'm going to take the map I get from the GIT potion from this representation variety, still of the torus. And then here, I'm going to be even pickier. My construction, I'm going to use the second tool, and this is this T representation variety. So just to recall, this thing is pretty complicated. This one is C star plus C star mod C2. And by the time I am here, I just have C star cross C star. My goal will be to build my knot invariant in here. Okay. So how I'm gonna do this? First what I'm gonna do is start with the image of iota star in here. I'm going to pull it back along this map. By inverse of this thing, I want to come in here. I'll think of this as a subset. So I'll restrict this RT the torus. And then for good measure, I'm going to take the closure so that this is all in C star. And let's name this thing V sub K. So now I have a variety in here. What I'm going to use. Sorry, it's a little short. Okay. So now what I want to use.
I fell.
Well, never before though. So finally, I want to use some algebraic geometry. Get an actual polynomial out of this. So the fact that this includes in here means that the regular functions on C star act on the functions of VK. And in particular, this is going to look like this original algebra mod some ideal. This thing here is polynomials in two variables. This thing here turns out to be a principal ideal. And here's my definition. By Cooper, Fuller, Newman, Long, Shalin, 94, no, 96. So this is after normalization. A of LM. Polynomial. Okay. So it's exactly this generator here. Any questions?
So is the hard part showing that that is principal?
That there's like a little thing. The hard part is showing that this is actually a not invariant. This is part of it. It's not that bad. These papers, which come ask me afterwards, because you just can't Google a polynomial and find this. Although I try every year. Yeah, these papers I would say are like pretty readable. It's not like an insane construction. Cool. So this is our invariant. But when I was writing the title of this section, I've had a little hat up there. And what this means is that I want to work with a quantization of this thing. So now what I want to talk about is how I take this whole construction and write down a non-commutative version of it. Yeah.
So your A polynomial is the generator.
Yeah,
And
so
the
it's,
ALM is the hat.
huh?
Is the ALM, is that a hat?
So ALM will be quantized to some A hat, like capital L, capital M. Yeah. That's a good question. So I'll just say quantization has different meanings in different parts of math. For me, what it's going to mean is I have some commutative ring. There's commutative algebra, and I want a non-commutative algebra with the parameter q. When I send q to 1, I get the original thing back. just to be concrete. That's what I'm looking for. My notes. And in particular, the thing I want to start talking about quantizing is this space here. When I say we want to quantize it, what I mean is I want to quantize functions on it. Oh, hi, G. Let's search this. Okay, we've already seen this ring before. It shows up a lot. It has some nice descriptions. I will go over this again. First thing I'm going to use is that the functions on the character variety, the character variety is a GIT quotient of something. These look like functions on the representation variety, which are G invariant, conjugation invariant. And let's just say it was our homework problem to start writing down functions here. How would we maybe start this? The first thing I'm going to do is remember this is a Hom space. So if you're looking at functions on Hom space, you have a really nice first start. It's evaluation. Okay, so I'm going to start with evaluation. And what this is going to look like is I'll take some loop on my surface. And I'm going to define a function from Rg of sigma, the G. And this is really, like I said, I'm just going to evaluate it. Right, so this is a nice function, but I'm only in G, and here I need to be in C. I'm not done. The next thing I'm going to do is I'm going to use trace, which is nice and maybe obvious because I need something that's conjugation invariant, and trace is famously conjugation invariant. But to get trace, I need to take my reductive group G, and I need to really understand it as matrices, right? Like I'm really going to demand that it is a matrix group for real, a particular one. And then from here, I could do trace down to C. And then together, let's call this whole construction together tau sub gamma. And then there's a theorem we've seen. Chuzzy gave it first, but if you're interested, the other people I would look at is look also generalized at some, Nache generalized at some, Sikora generalized at some. So if you need these facts, these are the names to look up. And in the case that we need is that the tau gamma with V, the fundamental rep, these generate this ring of functions. For DSL in C, I think it's also known for GLN. That's some others too. Or I guess for SLN, you need graphs. It's just to be super secure. SL2, that's all I need. So I have this nice explanation. Let's look at what's going on topologically here. Lush genus 2 surface. So let's start drawing homotopy classes on the surface. So say I have something here, U, or a loop, and it's colored by U. Let's see, what function does this look like? So if I take any representation and I evaluate it on this loop here is just the unit in my homotopy group. So this has to give me the unit on G, right? And then when I take the trace with respect to this representation of the unit of G, this is just going to be my dimension of U. So what I can see here is something that's starting to look like a skein relation. And the skein relation is that this colored with U is just the dimension of U times the world where that doesn't exist. Okay, so that's one we see. There's another one, which will be less exciting, which is I can multiply functions, right? And so I can ask, what does this look like with these loops? And what it looks like with these loops is I can just draw both of them. Right? And my relation, if everything is commutative, is that sort of I don't have any height data. So I don't distinguish between the heights of things. Right? So this is what my skein relation looks like in this setting. And so my idea for quantization is I wanted to form this, the quantize. And we'll end up being forced into deforming the other one too, to get it all to work out.
What do you mean by this is commutative?
These are functions. These are just C-valued functions. Yeah. So if I start to make the weird leap of really thinking of these functions as colored circles on the surface, then this is how this is like the I've made there. Okay. Won't erase any of this. Okay, so let me recap this. And I'm kind of harping on this because I think it's like one of the big facts people know about skein algebras is that they quantize character varieties. And I think sometimes what doesn't get communicated in that is that it's somehow like they're perfectly made to quantize character varieties, right? From this perspective, like it's exactly what you need to deform this. For me, this is not a spooky fact. This is a really natural fact. Okay, so let's what I want to do is make this deform this the quantize more precise. So I'll say what I've shown is that this SL2C character variety of my surface, what this looks like is a bunch of copies of S1 into my shipping surface. So it's up to homotopy. And these are colored by just rep G. And then I have a relation here, which is that two of these, I'll call them links, are equivalent if these functions associated to them are the same. Right? Just, I'll say like a dumb relation is just saying I'm talking about the functions. I have the same function, it's the same thing. So how am I going to quantize this? The first thing I'm going to do is I'm going to replace rep G in this description with rep QG, the Riemann group. And the other thing I'm going to do is I'm going to replace this relation. And what's going to be there instead is my Rashid-Tigan-Taraya functor. So I'm going to use rep QT or rep Q G. Quantize the relation. So what does this look like altogether? So this is my definition of the skein relations. Or I guess in algebra. And first, let's talk about what it looks like for just a disk. So, I guess sorry, this is actually the skein relations. Sorry. So for just a disk, what I'm going to say is one of these finite sums, I of graphs, 1 to n, it's going to be equivalent to 0, if and only if the Rashid-Tigan-Taraya functor, AI, RT, I, if this thing actually equals 0. 1 to n. So this is what my skein relation looks like. I'll say David just wrote explicitly a skein relation in the last talk. That was for essentially this case rep Q SL2. So this is for a disk. next for a general surface, what I'm gonna do is I'm gonna apply the relation on anytime I have this thickened disk embedding on my surface. So I'm gonna apply it here. Okay. So these are my relations, right? This is the equivalent of this relation here. And my notation is going to be that in algebra of Q CC, my surface is going to be, now I want to rewrite this thing. Setting this is going to be embedded graphs. And this is going to be rep Q SL2 colored. Now it's going to be mod these scale relations. So I've told you how to quantize this. Yeah, I think it's time to tell you sort of what happens with these other pieces here. So what happens, maybe I'll erase a little bit so I have some room. So this one, we already saw in David's talk. This is the skein module of MK. And here I have a map of the skein algebra, or from the skein algebra of the torus. This is the action. Here, it's, I would say, takes a whole nother talk dedicated to the subject, but this also has a quantization in skein theory. But this is something that gets called the internal skein algebra. Internal skein algebra. And sort of it has a very nice categorical description. But the way I like to think about it, sort of the picture for how it looks is now my surface, I have to put a puncture on it. Surface. And my skeins are now going to be allowed to end in a disk near the end of that puncture, So say I have some skein, and then when I multiply two skeins, instead of sort of stacking on this way, what happens is I stack on this way. I push in from the boundary. So this is this internal skein algebra.
But then there
Yeah.
just as a last comment, we
Yeah.
push them.
Yeah, so the more involved version of the story is that actually we have an embedding of a disk near the boundary here. And the skein algebra of a disk is a monoidal category. The skein algebra of a surface generally isn't. And we hitchhike on that monoidal structure of the disk. Induce one has to do with the punctured surface. It's a nice construction, so I'm happy to talk about it. Yeah. So the last thing I want to talk about is this, which actually turns out to be quite a bit of new technology that you need skein theory wise to understand. So here I've written it as just I have some subspace, right? Which would make you think that perhaps what we're trying to recreate is a map between the internal skein algebras with these different colors. But actually, what we find that we're doing is, so I'm gonna grab one piece of chalk, is I'm using this subset to go from the space of things living in the G character variety of my surface, right? This was this VK that I absolutely erased. Here, and I want to push this forward. Understand this as something living in my T. Right, so really it lets me go from subspaces here to subspaces here. Just I intersect. Right, with this thing. And the correspondence that I want to quantize really is that these are associated with O R the modules. So I'll say I go from this to ORT modules. Right. This correspondence is already something we used for making the A polynomial. And how this needs to quantize, I'll draw my squiggly line, is that this is going from I look at the G modules and its internal this, and I get a functor from modules for the internal skein algebra coefficient in G to modules for the internal skein algebra coefficients in T. This. And this map here is what I'm going to be calling the skein module bifunctor. And this is something, now you see why I'm talking after David, that he already introduced the utility of thinking about functors associated with three manifolds, with some M3. So what this looks like in our case, the technology is I want M to look like a thickened version of my surface. So this is sigma times 0, 1. But somehow on this side, I want everything to be in the G world. So I have G here. On this side, it's in the T world. What I found, and I'll draw just to be dramatic in pink. But what I need here is a defect. And it turns out the data that helps me define this defect is associated to B the Borel. And how you can imagine this construction goes is if I have some three manifold here. So M, if I'll call it N, some three manifold. I have my action of my algebra just by including here. This is my thickened surface. And what that gets sent to is I take my same N manifold and I now glue on this defect thing. G. And now I have an action. And the same thickened surface, just colored by T. So this is the construction. So this is all G colored and this is all T colored. So I think maybe actually place that almost stopped. I'll say in this way, we're quantizing the A polynomial. And the idea that we have is that I take MK and I glue it with this defect thing. And I look at the skein module in here. Mod. This module is what we expect. Look like the skein algebra. Mod. It's a hat. So that's how but I think that's where I want to stop. That's what questions.
Thank you. There are questions for James.
I was wondering, so from here, can you point out where it's actually like really helpful that you have this description of the ring of regular functions on your character variety being generated by the evaluation.
Oh, yeah, so that's helpful in saying that the skein algebras are quantizing this particular ring of functions.
Okay, is it really essential?
I think it's essential for arguing that what we did here has anything to do with the classical A polynomial. Such an invariant exists. Do you want to say that it has? This classical one?
Right.
So that's how.
Okay. Could I just ask? My memory of that type of proof for it, I haven't seen a ton of those proofs, but like it really fundamentally uses this description of like the mapping class groups for surfaces as being generated by Dane twists. Is it accurate that maybe that is like something really essential there, or do you know if there are proofs that somehow don't ever encounter this fact? Or apply it?
I mean, like, these graphs are generated.
I guess proofs that the ring of regular functions is generated by these type of evaluation functions that don't use the mapping class group of the surface being generated by.
Actually, I don't know. I've absolutely taken this part kind of on faith.
Okay.
Like I haven't read the proofs.
No, thanks.
Yeah, I was wondering before you quantize when you have this functor going from a commuter ring module to another one. So that presumably is also done by module. Do you
Yeah.
describe it? So it should be infinite dimensional.
Yeah, actually, that's a good question. That's something I've been. No, yeah, it should be like absolutely this, yeah, this Eilenberg Watts thing, but I haven't written down what this is.
Okay. And I have another unrelated question, which is earlier the step where you would C star times C star, which is RT of T.
Yeah.
Inside C times C, so that step felt unnatural, but
To like take this closure.
because in general, if you have RT of a thing,
Yeah. So, I mean. Yeah, I agree. I include this because this is like part of the construction, but if you didn't do it, you would just get a Laurent polynomial.
right? And
As your invariant, and
is that still not in
that's
there?
okay. Yeah, that's okay. Yeah, it's actually, I mean, because the invariant, it's like the actual invariant is more this ideal that it generates than it. So, I mean, you can multiply by anything invertible and it's just as fine, I think.
Thanks. A couple of questions. So I started the talk you mentioned is the J conjecture. And it's having this perspective on the A hat polynomial is coming from past one. I mean, that sounds like you're quite close to
Yeah.
things that produce a vigilance polynomial. Because it
Yeah.
fixes the RP construction anyway.
This is exactly my, like the motivation for quantizing it in this setting.
I see.
It is in this.
I see. Yeah, this is something more about that, or is
I can say, I mean, I haven't. Mainly my focus has been getting on like a nice.
Mhm.
Quantization, to give you a sense of like kind of the excitement of this project, like. This being defined this way, these algebras have really strong excision properties. In particular, you can work with like triangulations, not compromised. So like, that's where the most of the project has been, is like you should be able to write Sage code. So like just spit out this quantization. But the idea, it's a good question, is this sort of this okay. This, I'll draw it in pink. Like this boundary. This thing here. This is what's quantizing this. Right? And then the colored Jones, there's an action, this action that I mentioned. It's sort of, if you have this core or this not, you have like this, I don't know if I need more or fewer colors. I have a T colored force here. Right, and so you can picture the action on the colored zones is really coming from inserting something here, right? And so sort of this part here is this, and this whole part is this what's getting what's extending is how do I say it? It's like acting on the colored zones. Like this is how you understand. And when you glue this all together, there's something that haven't worked out, but we expect there's some statement about invertibility of these defects, which would tell you that the fact that I am in G and I have this little T in the middle, this should look like just a G colored sphere in the end. It's quite trivial.
Maybe